In section 9.4, we're going to introduce a different type of product from the previous section. So the previous section we learned about the dot product. And that was a way of taking the product of two vectors that yielded a scalar, right? It just gave us a number, not another vector. So now we're going to talk about a type of product for two vectors that gives another vector, right? And so here's how we define it. It says if A and B are non-zero three-dimensional vectors, the cross product of A and B is this vector here, and it's defined by the magnitude of A times the magnitude of B times the sine of theta times n. Okay, so now n, you see it's bolded, right? So n is also a vector. In fact, it is a unit vector that is perpendicular to both A and B, both the original vectors. And so here's the picture you want to look at. So here's A, here's B. Maybe imagine those like in the XY plane, just to kind of give us a point of reference. If you take their cross product, then you're taking the magnitude of each times the sine of this angle that's between them, and that gives you a scalar, and that scalar you're multiplying by this unit vector n that is perpendicular to both of those, or orthogonal to both of those. Right? Now, one of the results of this, and actually one thing before I move on, it says this n unit vector, its direction is given by what's called the right-hand rule. And I'm going to explain that in the example below. And it kind of gives a description here, but I think it'll make more sense when you have a visual of it. Okay. All right. So one thing to notice is that the cross product is always orthogonal to both of those. And so a theorem that falls from that is that two non-zero vectors A and B are parallel if and only if their cross product is zero. Now, the way to make some sense of this is that if you have a zero cross product, and it's the zero vector, right? So if the zero vector is your cross product, then by the definition of a cross product, that means that the magnitude of A times the magnitude of B times the sine of theta equals zero. But of course, we just said that A and B are non-zero, so that the magnitude of A isn't zero, neither is the magnitude of B, so that must mean the sine of theta equals zero. And let's think about, when does the sine of theta equal zero? Well, that means theta equals zero, so that means there is no angle between the vectors, or I guess theta could be 180, right, if the vectors are pointing in different directions. But either way, that gives you zero for the cross product. All right, so for this example down here, this is where I'm going to explain the whole idea of the right-hand rule. So what we're going to do is we're going to have these two vectors just on paper. And what I want to know is, when I take the cross product of each of these, what direction is the cross product pointing? Meaning, is it pointing into the paper, or is it pointing out of the paper toward me? Right, and so that's what we're going to explain here. All right, so in order for me to demonstrate the right-hand rule, I'm going to have to actually have you see my right hand as opposed to just seeing the computer screen. So here's the example that we're working on right now, right? So we're trying to figure out what is U cross V and what is V cross U. And what direction does the cross product point? Now we know it has to be perpendicular to both U and V, right? So that means it's either got to be sticking out of the page toward us, perpendicular to this this legal pad here, or it's got to be going back through the back of it, right? But either way, perpendicular. So we know that, but what we need to know is it out or in? So the right-hand rule tells you that. So let's start with the one on the right, so the V cross U, because it's easier to do. So the right-hand rule says take your right hand, it's got to be your right hand, and stick the edge of your palm against the first vector. So, and it's going to be the pinky side that you're going to stick right here, and then you're going to curl your fingers through the angle. So you're kind of grabbing at the angle itself, and then you're going to look at what direction is your thumb pointing. Well, obviously my thumb is pointing out of the page, right? And so that tells me that V cross U is a vector that points out of the page. All right, now for U cross V, I'm going to do the same thing. I'm going to stick my right hand, the edge of my palm along my pinky. I'm going to put that on U, okay? Now, if I just start curling my fingers now, I am not curling through the angle. I'm not grabbing that angle, am I? The only way that I can get my fingers to grab that angle is if I spin my hand around to grab it, right? Let me show that one more time. So in order to grab the angle, I have to spin around to wrap my fingers through there with my right hand. And so what am I doing now? I'm pointing in to the page. So this cross product vector, the U cross V, would be a vector that's pointing out the back of my legal pad. So on this next page here, we're going to give an application of the cross product, and that is the application of torque. Okay, so you probably all heard of torque before, maybe when it comes to the torque generated in some sort of machine, right? You often hear about it talked about with, vehicles and things like that. So what is torque at its basic level? So what torque is, it's the cross product of a position vector R with a force vector F. Okay, and so we're going to specifically talk about this in the context of pulling on a socket wrench that is attached to a bolt on one side. So what we're kind of talking about here is, and I guess I can make a little sketch of this. So we've got our wrench, and then we've got our handle. Okay, so R is, or I should say the magnitude of R is the distance from here to wherever you're grabbing the handle. And then you're going to apply a force to it. Maybe you apply the force directly down, but maybe not, right? So the force could be in any direction. So, wherever you work on cars and things, you're, almost never pulling exactly down 90 degrees, right, from this R vector here, right? So if this is the actual R vector, a lot of times you're pulling at some sort of an angle depending upon the room that you have, right? So maybe that's your force vector. And so the idea is the torque generated by this action, the torque generated on the bolt is going to be R cross F, right? And so here's a little cleaner diagram than what I'm doing. So we have the vector R cross F. So imagine like out here is the handle, and then you're yanking on it, and in this instance, you're yanking on it in this direction, okay? But you can see why it kind of makes sense that we talk about torque here is because some of the force is in this direction. I think we all agree that pulling down 90 degrees is kind of the most efficient way to do it. And so we're taking the scalar projection of this vector F onto this, onto a vector that points straight down to get F sine theta, right? And that's where this part of the formula is coming from. But here's the other interesting thing, right? What happens when you, if I was to pull in this direction, right? So if I was to pull my wrench in this direction, that is going to tighten it, right? When you go righty-tighty, right, as everyone remembers. So if that's the direction you're pulling, you expect the bolt to tighten, which means it's going to head into the paper, right? Just as you would expect the bolt to head in when you pull righty-tighty, okay? So there's that concept of that, what you first learn the first time you ever pick up a wrench, that righty-tighty, lefty-loosey is you can see that here in this definition of torque and what direction that torque vector is pointing. All right, so let's do an actual example here. It says, suppose that you apply a force of 20 newtons on a wrench attached to a bolt in a direction perpendicular to the bolt. Which produces more torque? Applying the force at an angle of 60 degrees on a wrench that is 0.15 meters long, or applying the force at an angle of 135 degrees on a wrench that is 0.25 meters long. Okay? So which one of those is the kind of the better option? Which produces more torque for us? All right, so of course, what do we know here, right? We know that the magnitude of our force is equal to 20 newtons. And, you know, newtons is just the metric, the standard metric unit for force, for those of you who haven't had physics. So that's our force vector magnitude. And then I've got these two different situations. One, I have a wrench that's 0.15 meters long. And then the other one is 0.25 meters long. So the symbol for torque's kind of interesting. It's this tau. And it's a vector. So the first torque is going to be R1 cross F, right? But we know that that's equivalent to the magnitude of R1 times the magnitude of F times the sine of the angle between them. So the angle between those first two is 60 degrees times this unit vector. And that's going to equal, let's see, 0.15 times 20 is going to be 3. And then this is the square root of 3 over 2. And approximately that's 2.60 times n. Then my second torque, same idea, R2 cross F. So we have 0.25 times 20 times the sine of 135 degrees. And that's going to equal 5 roots of 2 over 2 times n, which is about 3.54 n. So what we can see here is that the magnitude of this torque is a lot greater than the magnitude of this torque. So we would rather have the longer wrench and pull at 135 degrees than have the shorter wrench and pull at 60 degrees. All right. So there's another interesting application of the cross product, and that is that it also ends up giving us the area of a parallelogram that is formed by the two vectors you're taking the cross product of. Okay, so strange and kind of off the walls that may seem, here's why it works. Suppose I have A and B, okay, and I want to know the area inside of this parallelogram. Okay, now you learned long ago, you don't have to take calculus for this, that the area of a parallelogram is simply your base times your height, right? So we know that. So if I look at this parallelogram here, what's my height? Well, if this is the angle between the vectors, then we know that we can find the y component, which would be the height, by taking magnitude of b times sine theta. So this whole idea of base times height is going to be, and let me actually call this length to not mix it up with this b here. So we know that area equals length times height, but our length is the magnitude of A, and our height is the magnitude of B times the sine of theta. All right, but what is that? That is our cross product definition without the unit vector over here, right? So in other words, it is the magnitude of A cross B. So that's kind of an interesting application of this whole idea of cross product. All right, so what can we do with cross products? Well, cross products are different enough that their properties are not trivial to talk about. So first of all, in most instances, we have commutativity when we're talking about addition of vectors, the dot product of vectors. The cross product does not give us commutativity. So when you switch the order of your cross product, it actually changes the sign. But you know what? That makes sense because remember what happened in our first example when we were trying to determine if the cross product stuck out of the page toward us or into the page away from us, right? They're going in opposite directions when you switch that order. This associative property with scalar multiplication does work, though. You can use the distributive property, and you can use it, kind of in both directions here on either side. Okay. All right, so what if I give you two vectors, though, and I ask you to come up with the cross product, and I don't tell you the angle, right? Because so far, all we have right now is this, right? That A cross B is equal to the magnitude of A, magnitude of B, sine of the angle between them, times n. So you need to know the angle between them. So what if I don't? So there is a way to compute the cross product without referencing the angle or the magnitudes. And here it is. Okay, so if I want to take the cross product of A1, A2, A3 with B1, B2, B3, then here's the formula here. You might think, okay, is that something I need to memorize? The answer is sort of. You have to be able to take a cross product of vectors in component form without writing down a formula like this. But I do not suggest memorizing this as you see it. Let me show you the technique that I would suggest you use. All right, so it goes like this. When you need to take a cross product, you're going to compute something called the determinant. Okay, that word at this point isn't too important. Some of you who've taken linear algebra will recognize it. So I'm not even going to get into that. Let me just kind of give you my personal method for doing this. Other instructors will show you different things, right? Your physics instructor might tell you something different. There's no right or wrong here. This is just different ways of thinking about how to do this. This one of my professors taught me when I was taking this same class, and he calls this the spaghetti method. All right, so what you're going to do is you're going to write ijk twice in a row, ijk, ijk. Then you're going to write the first vector in your cross product twice in a row, so a1, a2, a3, a1, a2, a3, and then the same thing with your second one below that, b1, b2, b3, b1, b2, b3, okay? And here's where the spaghetti part comes in. So this is called the spaghetti method, at least according to my old professor, because you kind of think of lying a spaghetti noodle across this. And so what you're going to do is in order to produce the I component of your cross product, you're going to start a spaghetti noodle here and let it go through A2 and B3. And then you're going to fold it around this way to B2, A3, and I. And so you're connecting up the I's with a spaghetti noodle. And so what that gives you is A2 times B3, and then you remember to subtract B2 times A3. Okay, so you're always going to put a minus sign in the middle. And then when it's time to do your J component, you do the same thing, but you connect up your J's with your spaghetti noodle. So JA3B1 connected up to B3A1J, and you put a minus sign between the reds and the blues there. And then same thing with the K's. Lay your spaghetti noodle down, A1B2 minus B1A2. And that's how you can get your I, J, and K components of your cross product. So don't memorize this. Lay out your vectors in this way, and then you'll be able to come up with it every time. So let's actually do an example here. All right, so example 3. All right, so we're going to take U cross V. All right, so our instructions were I, J, K, I, J, K. And then I'll write out 2/3, 1, 1/2, 2/3, 1, 1/2. And then 4, -6, 3, 4, -6, 3. Okay, so we have it all laid out like this. All right, so now I'm going to say U cross V is equal to, all right, and I'm going to switch my color here. So I'm going to start with my eyes, and so I lay down my spaghetti noodle. 1 times 3 minus -6 times 1/2. 1 times 3 minus -6 times 1/2. That is my I component, or my X component. All right, switch colors again here. Connect the J's. 1/2 times 4 minus 3 times 2/3. 1/2 times 4 minus 3 times 2/3. And then yet one more color here. So my K's. So my K will be 2/3 times -6 minus 4 times 1. 2/3 times -6 minus 4 times 1. And that's going to give me my cross product. So what do we get here? 3 plus 3. We get 2 minus 2, and we get -4 minus 4. So 6, 0, -8. Now, if you don't want to really write that much stuff out, that is perfectly understandable. So let me show you what you're going to do when you start to get comfortable with this and maybe want to take some shortcuts. So here's what I do, now that I've been doing this for a while. I just write out IJK. I don't write it out twice. And I still go ahead and go 2/3, 1, 1/2, and then I do 4, -6, 3. So the way to go about this, if you're not going to write it out this much, is you still start off the same way. You still go, right, 1 times 3 minus 6 times 1/2, and then you realize that as you go through here, there's nothing there, but it really comes to the other side like this. So, I grew up playing like, Mario Brothers and things like that on just the regular Nintendo system. And Mario Brothers wasn't like this, but there were games where if you ran out the right side of the screen, you would all of a sudden reappear on the left side, right? So, I realize that if you played video games, you were of a different generation than I am, but maybe you've seen something like that. So the idea is I'm running off the right side of the screen and I just end up coming back through on the left. And of course that still gives me this, right? And then for the j, right? So j times a half, but I'm off the screen, but where would I reappear? I'd reappear right here in the third row. And then what am I going to do? I'm going to end up with 3 minus 3 times appearing over here 2/3 j. Okay, and then you end up doing k as well, right? So I don't know, color green, I guess. K would be, okay, I am immediately off the screen. 2/3 times -6 minus 4 times 1 times k. So you'll just kind of get used to doing that, even though you can't see it all, you can kind of imagine it just reappearing on the other side, and so that's perfectly acceptable as well. So here's another example where we can use the cross product to help us solve a problem. So what they've done is they've given us 3 points, and yes, these points are in three-dimensional space, but I would recommend let's not get too wrapped up in trying to graph them, in an XYZ coordinate system. Let's just go ahead and, just make a sketch, right? I'm not worried about accuracy here too much. Okay, so let's say here's my points, and I'm not, like I said, I'm not worrying too much about accuracy. So we'll go PQR. All right. Now, they want us to find this area. All right, so we're supposed to find that area. All right, now, if we want to find that area, let's think about what we've learned. We've learned that if we have a vector here, and we have a vector here, if we take the cross product of these vectors and take the magnitude, then it's going to give me the area of this parallelogram. Okay? Which is not what we're looking for, but we do know that it's exactly double what we're looking for. So if let's call this one A and this one B, what I know is that the area of my triangle is going to be 1/2 the magnitude of the cross product of A and B. All right, so if I can just figure out what A and B are and take their cross product, I'll be good to go. But what we definitely can do is if you want to figure out the components of A, remember, all you have to do is subtract the terminal point and the initial point. So that means let's take P and Q. Q is our terminal point. So let's take 3 minus 1, right? So I'm taking this 3 minus this 1. 4 minus 1 and 3 minus 5. So that must mean A is the vector 2, 3, -2. And then the vector B would be R minus P. So that's going to be 1 minus 1, 5 minus 1, and 7 minus 5. So that'll be 0, 4, 2. And so then if I want to know what the cross product is, I, J, K, right? And I'll go ahead and write it out here. I, J, K. And so we'll put 2, 3, -2, 2, 3, -2, 0, 4, 2, 0, 4, 2. And so to compute A cross B, all right, spaghetti method, connect up the i's, So that tells me it's 3 times 2 minus 4 times negative 2. Connect up the j's, negative 2 times 0 minus 2 times 2. And then connect up the k's, 2 times 4 minus 0 times 3. Okay, so then we can clean that up. So our cross product is, so we got 6 plus 8, so we got 14, negative 4, and 8. But of course up here, what do we need? We need the magnitude of that, right? But we know how to compute the magnitudes of vectors, right? It'll just be the square root of 14 squared plus negative 4 squared plus 8 squared. And that's going to give me, well, actually, I don't know exactly what that gives me under the square root. Didn't bother to write it out. 14 squared plus 16 plus 64. So under that square root, we get the square root of 276. So then over here, I'm going to say this is 1/2 times the square root of 276, which is approximately 8.31. So 8.31 square units is going to be the area of that green triangle. All right. So, we've been talking about what the cross product can do, and in large part, like that last example was in 2 dimensions, right? So this cross product is a 3-dimensional thing that we compute. It only applies to 3-dimensional vectors. However, at the same time, it gave us information about just the area of a triangle. Okay, but we might wonder, like, can this apply to volume? All right, so this introduces what we call the scalar triple product. So the answer is we can also get the volume of, it wouldn't be a parallelogram, but it's called a parallelepiped, which is just, think it's a 3-dimensional parallelogram. We can find its volume by taking the dot product of one of the vectors with the cross product of the other 2. Okay, so here's how this breaks down. First of all, if you have the area of this base here, so this is the A that they're referring to, and then the height of the parallelepiped, it makes sense that would give you volume. So area times height. But we know area, right? Area is the cross product of B and C when you take its magnitude. So that's the area. Okay, now the claim is that this is the height. Okay, so let's see if we believe that. So here's the height. Here's the vector A. So if I make this angle right here, okay, the angle between, and remember the cross product is going to stick up like this, right, B cross C. So the the angle between the cross product and the vector A is theta. So the height then would have to be the magnitude of A times the cosine of theta, because it's this adjacent side here. All right, so that's why that's our height. And if you look at this, if you have the magnitude of a vector times the magnitude of another vector times the cosine of the angle between them, then what you're going to get is the magnitude of the dot product of those 2 vectors. The reason we have magnitude here, by the way, is because when you do a dot product, right, sometimes it can be negative. Well, this cosine's also in absolute values, so this is always going to be a positive quantity. All right, so that's called the scalar triple product. So let's look down here at example 5. So the claim is we can come up with the volume of this parallelepiped that you see right here. And the nice thing is it doesn't really matter which vectors you pick for which role. So what I'm going to do is I'm just going to take, so we're going to go absolute value of 2, 2, 1, dotted with the cross product of 1, 0, 3, and 0, negative 2, 0. All right, so over here, let's go ahead and do that cross product. ijk, ijk, so 1, 0, 3, 1, 0, 3, 0, negative 2, 0, 0, negative 2, 0. All right, so down here we can go ahead and write this out. So this is 0 times 0 minus negative 2 times 3 is going to be positive 6. I'm going to do this a little bit quicker. 3 times 0 minus 0 times 1 is 0. Maybe I should be writing this out here. 6, so that was 0 times 0 minus negative 2 times 3. This 0 here was 3 times 0 minus, what did I say, 0 times 1. And then my k is going to be 1 times negative 2 minus 0 times 0, so negative 2. So that's my cross product. So b is equal to 2, 2, 1, dotted with 6, 0, negative 2. And then the dot product compared to the cross product is real easy, right? 2 times 6 plus 2 times 0 plus 1 times negative 2, which is going to give me 12 minus 2. So that gives me a volume of 10 cubic units.